Good afternoon, everyone. Today we are here for Mr. Gregoire Ky. He will be presenting on introducing quantum methods and tools to ATM. Mr. Ky graduated from the French National Engineering School of Electricity and Mechanics in 2017. And after that, he graduated from the Hong Kong University of Science and Technology in 2018. Furthermore, he temporarily worked at ONERA, the French aerospace lab, on numerical models applied to meteorology. Before joining ATMRI, he had worked for a few months at CESA Joint Undertaking, SJU, where he was in charge of designing a new automation roadmap for air traffic control systems. Today, he'll be talking about quantum computing. Quantum computers are generally expected to greatly enhance the processing capabilities of current computers. However, this transition has not been as smooth as expected. The purpose of this presentation is to introduce some of the tools in order to start exploring new ways of applying quantum methods to machine learning. So without much further ado, let's put our hands together and welcome Mr. Gregoire Ky.
Thank you, Kiran. Thank you everyone for coming. So, as you just mentioned, today I'm going to talk to you a bit about quantum physics, quantum computing. But just before we start, I just want to make one small thing clear. As some of you may know already, it's a complex domain. And what I'm going to present to you right now is something, is what I understood and my interpretation of quantum physics. So there might be, I won't deny that there might be some differences here. So now, if I say quantum, when you one of you here, what do you think of?
Ant-Man.
Particles.
Yes.
Ant-Man.
Yes. That's what I thought. What? Good call. We'll talk about that later. The thing is, when you think, for example, about pop culture, quantum is generally used as a buzzword to explain something that is too difficult to explain. Well, that's actually how I just sees it. It's actually supposed to explain something while not explaining anything, just saying it's quantum.
Okay.
The thing is, behind quantum, there is actually a lot of things. And even though in research centers it might look like a scarecrow because it's complicated, there are actually lots of things we can do. And especially, I think for most of you, you're looking forward to quantum computers. Am I right?
Mm-hmm.
Because you're probably thinking that when quantum computers are going to be released in the public, we're going to use them for our AI agents, and they're going to be far more powerful, far faster. Sorry to break it up to you, but reality is disappointing. I mean, no. Technically, it's going to work, but it would be like feeding a lion with grass. I mean, technically it can work, but it's a waste of resources. Not that I tried though. No. So that's why today I'm going to talk a bit about this, because there is far more behind quantum computers. And if you really want to harness the full power of quantum computers, then yes, you're going to have to do some quantum physics at some point. At least a bit. So what I'm going to do today is to give you an overview, brief overview of what's happening regarding quantum computers. So to start with, I'm going to introduce to you the core principles of quantum physics. The first was mentioned earlier, is superposition, and the second one is entanglement. Next, I'm going to show you some methods that maybe you can already use in your algorithms, in your programs. For example, you can use a quantum gate and quantum circuit representation, similar to logical or electrical circuits. Or you can use Grover's search algorithm, which is an algorithm made to search an object in a register with far less steps than what a normal computer does. And finally, we're going to have a brief look at applications. So to start with, applying quantum mechanics to machine learning, the links between them. I will briefly talk about this, and then I'm going to talk about quantum annealing, a special method that is actually extremely popular at the moment in research for optimization started. So, when you think about logical computers, you think about binary codes or bits. So bits, as you may not know, is a code made of 0 and 1. What the 0 and 1 mean, as written here, it's either a 0 or 1, it's true or false, right or wrong, yes or no. In that way, that's how logical computers work. They're extremely deterministic. But for example, let's do something. Try to guess, how many fingers do I have?
3.
3? No.
4.
No. 5? Yes. But did you see what you did there? You asked for each number what it was, and I only answered by yes or no. Is it 1? No. Is it 2? No. Is it 5? Yes. And that's exactly what a computer does. But of course with hundreds, thousands, millions of numbers. Exactly what it does. It's extremely deterministic, and it only answers by yes or no. But when it comes to quantum, it looks like this. Well, it looks a bit scary at first, but what we have here is that we have a quantum object that is both 0 and 1 at the same time. And we have A and B here, that are the weights of the 0 and the 1, that are complex amplitudes of the 0 and the 1s. And if you take the modulus of A and B, you have like the real probability of obtaining 0 or 1. That's why we have the sum here goes to 1 at the end. To make a 3D representation of this, it will look like this, like a sphere. This is called the block sphere, by the way. But I won't go into too much detail about that. So this principle of having both the 0 and the 1 at the same time is called the superposition principle. As a matter of fact, there is an experiment, an old experiment that I'm sure all of you have already heard before, Schrodinger's cat. Is everybody familiar with Schrodinger's cat? Yeah. So you have a cat locked in a box with a radioactive element that it can activate, and the idea is to know whether the cat is dead or alive. But since we cannot measure it, we don't know. So the answer to the question, the cat is dead or alive, is both. It's both dead and alive. It's both 0 and 1. Both yes and no. If you want to give it go into the philosophical way, it would mean that instead of just keeping it to yes, no question, you can actually add the maybe into computers and physics. So, if we go back to our quantum object from before, as I said with the cat before, we cannot measure it. But what we want is to measure it, because when we don't know, well, we're afraid of it and it's difficult to work with. Problem is, if you want to measure a quantum object like this, a quantum state, well, you're going to have either the modulus of A or the modulus of B, but in any case, you won't have all the information, at least in a single measurement. This phenomenon is also known as the wave function collapse. You cannot measure everything in a quantum state in one single measurement. It's because of that. It's actually, a measurement is actually destructive regarding a quantum state, because the quantum state afterward is not quantum anymore. It's logical, it's a real number, and it changes everything afterwards. In a sense, you could say that what you measure is just a small aspect of the quantum object, but the reality of the quantum state itself is that big. So, is everything okay so far? I'm going to talk about quantum states that I mentioned a few times already, what they are, really. But to start with, they're the solution of Schrodinger's equation that you can find here. With I, the imaginary number, small h, the reduced Planck constant, and h, the Hamiltonian of the system. But I won't use it again in this presentation. And the quantum state is generally written like this. It's exactly the same as we had before with the 0 and the 1, the A and the B, except that this time we are having ky's and ci's. So the ky's are the basis vectors of the space we are working in, and the ci's are the complex amplitudes relating to each vectors. But you are thinking, nah, yeah, but it's only 0 and 1, yes or no. Why are we supposed to have more? The thing, when it comes to this, we are working with qubits of quantum or quantum bits. So the basic unit of information, and they actually define the space we are working with. A qubit, if you're working in 1 qubit space, yes, it's like this. It's like we had earlier. Working in 2 qubit space, you have 4 different vectors with 4 different amplitudes here as well. 3 qubits, it goes to 8. And it goes on. And you have at some point, if you take n qubits, you have 2 power n different vectors, quantum vectors in your space. Which means that it is technically a bit more complicated to work with. So now, on to entanglement. So, before we start about entanglement, as you may have seen before with the qubits, we try to write the quantum states in what we call the separable states, which means in a sense of a factorized version of a quantum state are easier to process. The thing is, generally, it's not the case. Not a lot of states work like this. And so we have what we call an entangled state, which can be written like this, but it's a sum of only 2 terms, but it can be more, of course. Visually, it looks like this. What does it mean, though, is that if you, for example, push one object, it will directly influence the other. So let's have a representation of how it can look like. So you have here, you may have seen, both lamps went down, while only one of them had a crash onto it. So in a sense, we could say that the lamps were entangled together, although I don't know exactly the physics behind what happened here, but you could say that both lamps were entangled. If we want to go back to ATM for a while, and as an example, imagine you have a storm over Japan, and that it will directly, you will find a correlation, and it will actually induce delays in Mumbai, for example. In a sense, having entangled states means there is a correlation between the different states in this same one. Okay? Alright, now I will switch on to quantum methods to have a look at how you can apply those principles to something that you might be able to use. So now, this is a quantum computer from IBM. As far as I know, the biggest quantum computer that was created is 20 qubits, which might sound not that big compared to what we have with larger new computers, but as I said before, 20 qubit means you have 2 power 20. Just thinking about that number scares me, so it's already a big processing number, and it's already extremely powerful, just 20 qubits. But the thing is, what a quantum computer does compared to a classical computer is actually, instead of having one input code and modifying it to obtaining another at the end, it takes all vectors and inputs, and it returns and others. And they are all linked to each other. If you want to try a representation, a circuit representation of that, it looks like this. So you have one input, one output, and the circuit behind, or the gate for that, gate or the circuit for it, if you correlate a certain number of gates. The thing is, you can represent the whole circuit gate by a single matrix. A matrix that will be a 2 power n times 2 power n in terms of size. But because we have the sum of the probabilities equals to 1, it will become, well, there are other reasons as well, it will become unitary. You have an idea of what does that mean for a program? If it's unitary, it means it has an inverse, so it means the circuit is reversible. So you could imagine for a program, you can go from the data to the result, but you can also go from the result to the data. And actually find if there is a slight difference in the result, try to go back to the data. Since all quantum circuits are reversible, technically it is possible. Complicated, sure, possible. That's a typical quantum circuit, so that is just to give you an idea of how it looks like, with a certain amount of gates. Those are called the Hadamard gates that transform zeros and ones into averages of other vectors, of the other vectors. Now I'm going to switch to Grover's search algorithm. So it's an algorithm that was born in the mid-90s, so not that long ago. And it's a search algorithm. I won't go too much into the details here. I can only refer you to the original paper about this. It's a search algorithm, so instead of looking, imagine you have a register of objects, for example, phone numbers. So they are not sorted out. You have one phone number, you want to look up the name of its owner in the register. If you want to do that with a logical classical computer, depending on the size of the register, it can take a certain amount of time. You have to check each and every single phone number one after one. What this algorithm does is that it writes every phone number, every item of the register is inscribed into a quantum vector, which forms a quantum register or quantum database, if you want. And that it works on the whole database at each time. It removes the item we're looking for from it 2 times, averages, amplifies, and does it and it loops. It does it again and again and again. The idea is that at some point, when you measure the register, the only probability you will get is the one of the object you're looking for. It might sound complicated like that, but it's actually far more effective. But in computer sciences, they use this notation, like your square of n, so which means it's a quadratic speedup. Something that will, if I want to make a certain analogy, if you want to look for one object in a 10,000, one object in a register of 10,000 objects using a quantum computer, in terms of time, it will be the same as looking in with a classical computer in a 100 size register. Going from 10,000 to 100 is a consequence speedup. As a matter of fact, this algorithm is one of the most commonly used algorithms in quantum computing in general. As we will see now, moving from application, I'm going to talk briefly about machine learning. So I'm sure those of you who are working in machine learning are probably familiar with the names on the far left, names on the methods. What this table puts into perspective is that for each of these methods, there were already works that tried to give each of those methods a quantum twist. Try to give them a new quantum way of doing the things and actually try to study what it can change afterwards. We have the second column from the left is the reference, and then the third column is actually whether the quantum method uses Grover's algorithm or not. The one I just mentioned, just introduced you before. And afterwards, the next column talks about the potential speedups it can obtain from this. last column, there's one about quantum data, so that is also something that needs to be taken into account. And one of the issues of the moment is to make sure that the data you want to use in your machine learning method is in a quantum state, which is not necessarily the case. And by using conversion and by converting it from a normal to a quantum state, we'll need more processing time as well. Now, I will try to introduce you briefly to quantum annealing. So annealing, as you may or may not know, is a metallurgical process. So that has nothing to do with quantum physics at first. But when you look at it, there are some companies like D-Wave, for example, that created annealers a few years ago, and a machine that uses a system of quantum tunneling to find the minimal value of an objective function. As a matter of fact, quantum annealing is already extremely popular, and there are already works, research that is done on trying to apply quantum annealing to ATM related issues. As you can see here, you have two papers from earlier this year, that are trying to do just that. One for deconflicting optimal trajectories, and the other one for flight gate assignment. But that is why it is a trending topic. There are lots of works using quantum annealing, but some of them are ATM related, not all. But there are lots of possibilities. The thing about quantum annealing is that you don't necessarily need to be a professional of quantum physics to use it. What happens in those papers, and in all those papers that try to use quantum annealing, is that they want to try to map their problem to a certain model that can be directly applied into the annealer. This problem mapping is called the quadratic unconstrained binary optimization, or QBO. What it consists of is finding the minimum of an objective function of binary variables, and yeah, it looks like this. The idea is to try to write your problem in this form, find your matrix Q, then map it to the annealer, press send, and wait for the results. Well, it's more complicated than that. There are a few more steps in the process, but the main core of the papers is around this, modeling the problems to the QBO. All right. So far, that's I've been around what I wanted to present to you. I hope that right now you were able to not be scared anymore of quantum physics, and that maybe thinking that it might be interesting to give a quantum twist to perhaps what you're already doing or what future work you might go with. Because there is so much to gain by trying to go quantum physics. And when quantum computers are going to be released, it would be a shame to just feed it grass instead of using its full power. Thank you for your attention.